So like he said, I'm going to be talking about, my talk is called Theory of Neural Networks, and the alternate title would be Deep Learning Without Frameworks, because I'm going to be talking about the basics of deep learning and neural networks, but I'm not going to be using any framework. So I'm not going to be using Keras or TensorFlow, and the whole point of this talk is to hopefully help you guys understand how deep learning and neural networks work kind of under the hood. Because usually when you're working with these things, you're going to use a framework that kind of hides a lot of the implementation. So hopefully after this talk, even if you're completely new to deep learning and neural networks, you'll have a better understanding of how those things work. And so the first part of my talk, I'm going to be going over some of the basic concepts and showing how things work. And then I have a second part after lunch where I'm going to bring it all together and do some live coding and show you how to solve an actual problem using just straight Python, and showing you how to create a neural network from scratch. So first, a little bit about me. Let me get my... There we go. So my name is Beau Carnes, like you heard, and I am from the United States. I'm from the state of Michigan, and I currently work at freecodecamp.org. It's a nonprofit with the goal of providing a free curriculum for people learning software development, and so anybody can go on and learn for free. So like a new thing that we're doing over at Free Code Camp is we've translated the curriculum into 5 different world languages, and we just use the Google Automatic Translator, but we are an open source community, so we're trying to get people to go in that are native speakers and fix the automatic translations, and Russian is one of the languages, so if anybody's interested in trying to help out this open source community and you speak Russian, you can go in and help with the translation. Besides that, I also have made some courses for this book publishing company called Manning Publications. I saw on the booth out there, I saw some Manning Publications books, and I've created some video courses. So I have one called Algorithms in Motion, and then Grokking Deep Learning in Motion. So the second one is kind of the Grokking Deep Learning in Motion. That's what this talk is based off of. And the whole course, the whole video course is actually based on this great book by another author named Andrew Trask. So I would highly recommend this book for anybody trying to learn deep learning. So my video course is based on the book, and this talk is based on the course. So let's kind of get into it here. First of all, I wanted to tell you that I do it. So this is my personal website, carnes.cc, and then I made a page called Moscow. So all my slides are on there, and all the code that I'm going to be going over during this part of the talk and the second part of the talk. So you don't necessarily need to look at it now, but if you ever want to refer to that, you can. And so I'm going to be going into more detail into code than some of the previous speakers. So sometimes it's good to see the actual code. So deep learning versus machine learning. So deep learning is actually a subset of machine learning. So if we go here, you can see that we have machine learning, and then the subset is deep learning, and then the subset of that is artificial intelligence. So machine learning is kind of like what it sounds like. Machines or computers are trying to learn something that they were not explicitly programmed for. So machines observe a pattern and attempt to imitate it in some way. So machine learning is often attempting to take an input data set and transform it into an output data set. So let me show you some examples with an input data set and an output data set. So these are all examples that you would use machine learning or even deep learning to try to figure out. So if you have pictures of a cat, you have the input is pixels, and then the output would be a presence or absence of a cat. So you input the pixels, and the output of the algorithm would be whether or not there's a cat there. And the next one would be you could input movies you liked into the algorithm, and then it would output movies you may like. So these are just some different possible use cases. You would input words, and then it would output whether those words indicated that the person was happy or sad. And then you would input weather sensor data, and the output would be the probability of rain. So these are all supervised machine learning tasks. And the machine learning algorithm is attempting to imitate the pattern between two data sets in such a way that it can use one data set to predict the other data set. So I'm going to give you a summary of how machine learning would do that and how a deep learning algorithm would do that. Let's say you have this data set of pictures, and a lot of the pictures are pictures of cats, but then some of the pictures are not cats. So how it would work is you would input all these pictures into your algorithm, and you would also tell it which pictures were cats and which pictures are not cats. So the supervised learning algorithm is going to extract patterns from that data set. After it's learned the patterns, we can show it a picture, and the algorithm will hopefully tell us whether the picture is of a cat or not. So it takes all the information you give it, and then hopefully later you can give it a picture of a cat that it hasn't seen before, and it will be able to figure out whether it's a cat or not. So deep learning is a subset of methods in the machine learning toolbox that uses artificial neural networks. So let's get into more details about deep learning. Oh, here would be an example. Is this a cat? Yes, it's a cat. So all deep learning and machine learning algorithms are going to be classified as either supervised or unsupervised learning. We take what we know and we transform it into what we want to know. So that would be a supervised learning. We have something that we know to be true, and we transform it into what we want to know. So like an example would be we know that this picture, we know that this is a picture of a cat or maybe not a cat, and we put into the algorithm to find out what we want to know, like whether really it is a picture of a cat. So the goal of a supervised learning is to learn a function that, given a sample of data and the desired outputs, best approximates the relationship between the input and the output in the data. Supervised learning is done using prior knowledge of what the output values for a sample should be. Like in the cat example, we know that the output is either going to be cat or not cat. Or maybe you're trying to identify handwriting, and you know it's going to be one of the letters of the alphabet. You know the alphabet. You already know what the output could be for supervised learning. So for unsupervised machine learning, we don't know what the output could be. We're just inputting a list of data points, and we put it into the algorithm, and then out comes a list of cluster labels. So we don't know for sure. So the algorithm is trying to figure out and sort the data, but it doesn't know what the categories that it's trying to sort into. So unsupervised learning groups your data. The goal is to infer a natural structure present within a set of data points, and we put in a list of data points, and we get the cluster labels out. So basically, an unsupervised learning algorithm says, find patterns in this data and tell me about them. So it's just trying to figure out some patterns. Let's see, that was slightly out of order. We'll get back to that slide. So this would be kind of an example of unsupervised data, where you have all these data points, and your algorithm groups them into these different groups. And so the algorithm basically says, hey, data scientist, I found some structure in your data. It looks like here are some groups in your data. Here are the groups. And then it's up to the data scientist or the programmer to figure out what the groups are. It doesn't tell you what the groups are. You just kind of have to figure that out after you see the groups. So The next thing I want to talk about is parametric versus non-parametric learning. And pretty soon we'll get to some actual code examples, so this will start to make more sense. But for this, you can just kind of imagine a cloud. So so this is our machine learning cloud. There's two knobs. We have supervised and unsupervised knob, and a parametric and non-parametric. So you can kind of switch your algorithm to be either supervised or unsupervised, parametric or non-parametric. Supervision is about the type of pattern being learned, and parametricism is the way the learning is stored. So the two types, parametric and non-parametric. Parametric is with a fixed number of parameters, and non-parametric is possibly an infinite number of parameters. So here's kind of an oversimplification. Parametric is trial and error, and non-parametric is about counting and probability. So you could have you're just kind of counting and you don't know how many parameters there's going to be in non-parametric. So let's do an example. I'm going to go back to this slide. So let's say you're trying to figure out, you have this square and you're trying to figure out where it should go in this little toy here. Now again, this is a pretty simple example, but some people, like a baby, may just jam it into every hole until they find out where it fits. So that's kind of like parametric learning. Now non-parametric learning would be you're counting the sides of the square and counting the sides of the hole, and then you kind of figure out where it will go in that one. So a parametric models tend to use trial and error, like just trying everything. A non-parametric tends to count to figure out where it should go. But most algorithms are supervised parametric learning. So for the rest of this talk and the next talk, I'm going to be talking about supervised parametric learning and giving you some examples to go along with that. So this is basically trial and error using knobs. And so there are 3 steps. Step 1 would be predict. So the 3 steps to supervised parametric learning is, the first step is predict. So for the predict step, you take all your data. In this case, we're trying to predict if a sports team is going to win a game or not. So we input this data like number of toes on the team, number of players, number of fans. We put it into our algorithm, which is our machine, and then out comes a prediction. So in this case, our prediction is saying that there's a 98% chance, given this data, that our team is going to win. So step 2 is going to be compare to the truth pattern. So we have our prediction, which is 98% chance that the team's going to win, and our truth pattern is we found out that in real life they lost the game, so 0% chance of they're going to win. So we thought our original prediction was 98% chance they're going to win, but actually they lost. So then after we compare to the truth pattern, this is where we are going to learn the pattern. So learning. When we're going to just take the information about how much we were wrong. So we look at how much we missed by, which is 98%, and we also look at the input data at the time of the prediction, and then we're going to turn the knobs. So these knobs will be weights. So the knob of the win-loss, the home-away, number of toes, number of fans. So based on all the information, we're going to adjust the weights, so hopefully the next time, the next iteration of the algorithm, we can be a little closer. Instead of 98% chance we're going to win, that number is going to be lower, because we know that in reality they didn't win with that information. Now, so now that you kind of know the basic steps, I know it's kind of hard to understand how all that fits together, but now I'm going to get into some actual code, so hopefully it starts to make sense what I was talking about with the predict, compare, learn. So this is a simple neural network. And a neural network is one or more weights which we can multiply by our input data to make a prediction. So it's all about trying to make a prediction on the correct answer based on those weights. So in the example that I gave, the prediction would be whether or not the team is going to win a game based on the input data and the weights. So here are our first few lines of code here. I start by just hard coding a weight number. Now, generally, your weights are going to start as random numbers, which we'll see in the live coding section later. But here it's just hard coded, so you can kind of see how it works better. And we have our neural network function. So we can see that our neural network function, we just pass in the input and the weights, and then it's going to set the prediction to input times weights, and it returns the prediction. So it's all about just multiplying inputs times weights. So this diagram kind of shows you how it works. You input the information here, multiplies by the weight of 0.1, and the prediction is the % chance that the team is going to win. So this next section of code, so we just talked about this part right here, but here is our data. So we have this array of number of toes. This would be like average number of toes for each of the first 4 games in the season. So it's kind of a silly example, but just kind of bear with me here. Our input is just going to be the first number, because we can only run it on one number at a time. So we're inputting just this 8.5, and then our prediction, we just call the neural network function, which multiplies the input times the weight, and then we get out the prediction. So it inputs, so we have the 8.5 times the weight. So our prediction is that there's an 85% chance that our team is going to win. So we can see that the prediction is the input times the weight here. So let's talk more about what the input data is. So an input data is a number recorded in the real world somewhere. So it's usually something that's easily knowable. Like in the example, average number of toes, it could be today's temperature, it could be yesterday's stock price. So it's just we're going to input some data that we can see in the real world, and then we are going to make a prediction. So here, just a second. Okay, so a prediction is what the neural network tells us given our input data. So like, given today's temperature, I think our network thinks there's a 0% chance that people are going to wear swimsuits today. Or maybe given yesterday's stock price, today's stock price is going to be 101.3 or something like that. Or given this many number of toes, this team is going to win the game. So that would be the prediction. And then the network learns through trial and error. So in that example, it only went through it one time. So in a real neural network, which we will get to, and I'll show you a network with a lot of iterations, every time it runs through the code, it updates the weight and it updates the error, and it keeps running through the code over and over to learn. So first it's going to try to make a prediction, then it sees whether it was too high or too low, and then finally it changes the weight up or down to predict more accurately the next time it sees the same input. So far we've seen the network making a prediction. So remember, the 3 steps were prediction, and then comparing, and then learning. So I still need to show you how you would compare it to the truth pattern and learn, and I'll get to that in a minute, but I'm going to show you another example before I get to the compare and learn. So here I'm going to show you a neural network with multiple inputs and outputs. So the first example, there was just one input and one output. In this example, we're going to have 3 inputs. So it will be like the number of toes per player, the win-loss record, number of fans will be the inputs. We're inputting all those things into the network, and then we're outputting the percentage of hurt players, whether or not the team is going to win, and whether or not the team is sad. So this is just kind of to show that I started with showing a very simple network, but they can get more complex. So you can have any number of inputs you want, and you can be trying to predict multiple things. You don't just have to predict one thing for the inputs. You can predict multiple things. So Here's all the code. Now I'm going to kind of zoom in so you can see the different sections. So first we're going to talk about the weights. So before, we just inputted one number for the weight. But now that we have multiple inputs and multiple predictions, we have to have a matrix. So a matrix is just an array of arrays, basically. So you can see the first line is the weights for number of people hurt. Second line, number of people that if we won or lost, and then percentage of sad. And then for kind of each column, we have the weights for the number of toes, what the win ratio is, and the number of fans. So then our neural network looks almost exactly the same as before. Remember before, we just multiplied the input times the weights, and that's what we're doing now, except we have this fancy function, vector matrix multiplication. Before we were just multiplying one number by another number. Now we're multiplying a vector, which is an array, by a matrix, which is an array of arrays, and so we need some extra code to make it so you can multiply a vector by a matrix. And we'll see that in a little bit here. So this is our information. This is our input data for the first 4 games. But for our input, we're just going to take the first number of each array. So we're just going to do kind of one game at a time. And so here's an example of what it would look like for what we're passing in our input data. And then we have all these predictions that kind of come out of the network. So I talked about the vector matrix multiplication function. I'm not going to go into this in great detail. It's just a way to multiply a vector by a matrix. But and this function kind of uses this weighted sum function. But in real life, you're probably never going to write these functions yourself because most people are going to use NumPy. So NumPy gives you just extra functions to do math, like multiplying matrices and and vectors. So this line right here from our neural network in NumPy is going to be like this. And when I do my live coding, I'm actually going to use NumPy, so you'll see how that works. So this dot here, that's a NumPy function. And this just means multiply the input by weights, and then we get the answer into our prediction here. Okay, so at the end of our network, we just set our prediction to equal the return value of our neural network, and we can print our predictions. So you can see here are our predictions that we printed out based on this network here. So if we go over here, you can kind of see everything on the screen at once, and then down here you can see the prediction. So you can see how the math is calculated, and so our hurt prediction was 0.55, so we think there's probably 55% of the players may be hurt, 98% chance of winning, and a 97% chance that people are sad on the team. So we can predict 3 things at once. So the next thing I want to talk about is error and gradient descent. So this gradient descent is used while training a machine learning model, and it's an optimization algorithm that tweaks its parameters iteratively to minimize a given function to its local minimum. So in other words, it allows us to calculate both the direction and the amount that we should change our weights, so we reduce our error. So the whole point of our neural network is trying to get our error to 0. So our gradient descent, which we'll see the code later, and it's pretty simple. It helps us figure out which direction we should move our weights and how much we should move our weight. So when we calculate the error, it goes down. It's just a way to, every time we run the code, every iteration, we're going to use our gradient descent function to get our weights to the right spot so our error goes to 0. So we talked about supervised parametric learning in the 3 steps. We talked about, but so far you've only seen predict. But now I'm going to show you how to do the second 2 steps, the compare to truth pattern and learning the pattern. So for the step 2, is compared to the truth pattern. To measure the error, we determine how far our prediction is from our goal prediction. And then step 3, learn the pattern. It takes our error and tells each weight how it can change to reduce it. So the whole point is trying to figure out which weights are impacting our error so we can reduce our error to 0. And by time when our error is 0, that shows us that our weights are accurate because there's no error. So now I'm going to show you, pressing this button here, hopefully it'll change slides. Just a second. Oh, wait. Okay, so learning is adjusting our weight to reduce the error to 0. So that's what we're trying to do to actually, that's what our learning is actually doing. So here is our one iteration of gradient descent. Now, in a real example, you could have like hundreds of iterations or thousands of iterations. And when I get to the live coding, I'll show you one with a lot of iterations. But let's just take it one iteration at a time. So first we get our weight and our alpha. And our alpha is the simplest way to prevent overcorrecting our weight updates. So sometimes the goal is to get our error to 0, but sometimes instead of our error going down, it will start going up. So alpha is something that's going to help it to always go down and go in the right direction. And you'll see later how that fits into our code. It's kind of trial and error for what alpha you're going to use, but it's usually a multiple of 10. So you would start with maybe 0.01, then you could try 0.1, and then you maybe try 1, and just try to see which one is going to make your error go down instead of up. So let's see. And then our neural network is the same as before, which is input times weight. And here's the diagram. So our input data goes here, goes through our weight, and then we outcomes our prediction, our win prediction. So now we are going to we're going to do our prediction step. So we pass in our information. You can see there's only a few things different here, which is our goal prediction and error. So we didn't talk about error in our last code, but that's very important because we're trying to get our error to 0. So right here, we see that we have our number of toes is 8.5, just like before. Our input is our number of toes. Now our goal prediction is our win or loss binary, which is a 1 means that the number 1 means that they won the game. So our goal prediction is 1. So we think that with the input of 8.5, the goal prediction is 1, that they won the game. So we do our prediction just like before with our neural network. We multiply the input times the weight, and then our error is going to equal prediction minus goal prediction square. So this is prediction minus goal prediction is the raw error. It's how much we predicted was going to happen minus what we thought was going to happen. And then the reason why we square it, it forces the raw error to be positive by multiplying by itself. So a negative prediction, a negative error wouldn't make sense. So when we square it, it's always positive, and it also has the added benefit of making large errors larger and small errors smaller, which actually helps our neural network to go quicker to the correct to the correct thing by squaring it like that. So if we run our neural network, we do the 8.5 times 0.1, we get the 0.85, but then our error ends up being 0.023. Okay. So then we have our delta. So this is the compare step. We're going to calculate our node delta, and the delta is how much this node missed. So that's the raw error, prediction minus goal prediction. So we need to know how much the node missed, so we can calculate, we can kind of put it into our output. So we know we missed by negative 0.15 because our prediction was 8.85 and our goal prediction was 1, so 0.85 minus 1 is negative 0.15. So weight delta, this is where the gradient descent happens. So you can see it's actually a pretty simple line of code. It's how much this weight caused the network to miss. So we want to find out, we know that we missed, but how much did we miss? We just use the weight delta, which is just the input times delta gives us the weight delta. And we're trying to figure out how much to update the weight, because we're trying to change the weight on every iteration. Now this actually does 3 good things for us. It helps us with stopping, negative reversal, and scaling. So stopping, it's the first effect on our pure error caused by multiplying it by our input. So just imagine you're listening to music, or you're playing music on your computer, or you're trying to play music, and you have speakers. So you turn up the speakers all the way, but music still isn't coming out because you forgot to hit play on your computer. So this would kind of be an example of stopping, where it kind of addresses it in our neural network. So if our input is 0, like you forgot to press play on your computer, it will force the weight delta to also be 0. So we don't learn when our input is 0 because there's nothing to learn. And so moving it makes no difference. Then negative reversal, when our input is positive, moving our weight upward makes the prediction move upward. But if our input is negative, then all of a sudden our weight changes directions. Now we only want our weight to go in one direction. So when our input is negative, then moving our weight up makes the prediction goes down. We don't want that. So multiplying our delta by our input will reverse the sign of our weight delta in the event that our input is negative. So this is the negative reversal. This ensures that our weight moves in the correct direction. Scaling is just when anytime you multiply things together, it's either going to get a lot bigger or a lot smaller if the number is less than 0. So this is good because we want our weight delta we want big errors to be really big and small to be really small. And alpha is going to help it so it doesn't go out of control. So we don't want it to get too big. That's why we have the alpha, which we'll just about to talk about here. But first we can see how the weight delta, it kind of gets applied to the weight here of negative 1.25. Okay, so now we're getting toward the end of this. We are going to update the weight. So when it says weight minus equals, that just means weight equals weight minus weight delta times alpha. And so we're going to multiply the weight delta times the weight, or we're going to do weight minus the weight delta, and we multiply it by the alpha to control how fast the network learns, because it can, like I said, it can update weights too aggressively, but the alpha is going to, remember the alpha in this case was 0.01, so it makes it so the weight doesn't get updated as quickly, and so it doesn't get too out of control. So in this case, the new weight is 0.11275. So we're actually getting toward the end of the first part of the talk. I know this is kind of a lot of information all at once, especially if you're kind of new to deep learning. So my hope is that in this part of the talk, I gave you some good foundations and background knowledge, so when we get to the second part of the talk, you'll be able to understand how it all goes together. So in the second part of the talk, we're going to use everything we've learned, but we're going to use a real problem, and I'm going to live code a full neural network complete with iterations, so you'll be able to see how the weight updates, you'll be able to see how the error updates, you'll be able to see in the output of the neural network how the error is going to 0, and hopefully all these things we've kind of talked about that you've seen for the first time will start to make more sense when you see how it all works in an actual neural network. So we'll also, in the second part of the talk more about the deep learning part of this. So far I haven't even talked about why it's called deep learning, but that's something else we'll be talking about. So I guess that's all I have for this part of the talk, and I'll kind of open it up to questions if you guys have any questions about what we've talked about so far.
Sorry.
Yeah.
It's a stupid one. Then didn't really understand how my data will change sign. So how how it will become positive instead of negative.
Okay, so
Can you just back up a bit?
It sounds like you're asking how, when I was talking about the negative reversal, how it would go from positive to negative. Okay, let me go back to the code here.
Yep. So for instance, if like our weights are positive and our delta is negative, it will just go down and down and down, no?
So yeah, so if our input is negative, if our input starting out is negative, then once we calculate if our input is negative, then probably probably our delta will be negative. So I guess that's something I wasn't. So we want our weight delta to be positive. So if our input was negative, then our delta was also negative. So when we multiply the input times the delta, we have two negative numbers. We're multiplying it together, and the weight delta ends up being positive.
Yeah, that makes sense. Thank you.
Okay.
Thank you. Returning to the start of speaking about supervised and unsupervised learning. I understand that we change what learning we use from our data set. Is it marked or not? Yes?
Can you ask it one more time? Can you ask the question again?
We use supervised learning when we have a marked data set, and unsupervised when it is not marked.
Oh, yeah. So when you know what the data set is and you know exactly what you're trying to figure out, then you would use supervised learning. Like if you're trying to figure out what a number is, if you're doing like handwriting recognition, you would use supervised learning because you have this letter and you know you're trying to figure out this is a letter, so that would be supervised learning. But then if you don't know what you're trying to figure out, you're just trying to get your algorithm to figure out some patterns in your data, that's when you would use the unsupervised learning.
Yes, and a question. You told us about supervised learning and compare with the truth pattern, and how check how accurate our predict in unsupervised learning.
Okay, so you're saying, the question is about how you would check about the truth pattern unsupervised learning.
Yes.
Well, so unsupervised learning would be a little different where the 3 steps I was giving you were just for supervised learning because that's one of the most common types. So for unsupervised learning, you're not going to compare to the truth pattern because you don't know what the truth pattern is. So you would just have a different type of algorithm that's going to be able to kind of compare the data to itself to figure out the groups that it should be in. So hopefully, I know that's kind of a general answer to your question, but hopefully it kind of gives you enough of what you're asking about. And so that would be kind of almost a whole nother talk to see how unsupervised learning worked.
This one is a bit complicated. So, when you do unsupervised learning, one of the main questions is how you define the number of clusters. Like in text processing, there are like some numeric metrics that you can use to kind of assess how well your model performed. So my question is, can you in theory use deep learning to the task of splitting the clusters different ways and see how they perform, something like that? So can you use deep learning to find the number of clusters?
Oh, okay. So the question is trying to figure out how many clusters there should be by using deep learning.
Yep.
Yeah, actually, there are some deep learning algorithms that combine supervised and unsupervised together, and it kind of sounds like that's what you're talking about, where you could use like unsupervised learning to divide into clusters, and you could use supervised, and then after you know the different groups, you could use the supervised learning to go through additional data to figure out, to get that data into the same groups as before. But yeah, you could use some algorithms to kind of figure out the exact number of clusters to do, and it's really trial and error. A lot of deep learning is trial and error, where you try, if something doesn't work, you just kind of adjust your code a little bit to try something else. A lot of the numbers that are in your deep learning algorithm, like the weights and different things like that, you just kind of have to try different things until you see some information that makes sense to you.
Thanks.
Any other questions, or maybe more questions after my second talk, because you'll kind of see how it works all together. So then you'll maybe have even more questions, since you'll understand it a little more. Yep. So I'm glad to see so many people decide to come back to part 2 of my talk. So this is where I'll be pulling it all together, what we were talking about in the first talk, and hopefully a lot of things will start to make a lot of sense once you see a full neural network based on trying to solve a problem. So I am going to be doing some live coding in this section. You can try to follow along, or you can just watch at the screen. It's kind of up to you whether you have a computer or not. The second part of the talk, I will be just showing some code that's already typed out. And so again, kind of like the code segments in my first part of my talk, I have a link to that full code on my website, carnes.cc/Moscow. So if it would be helpful to see all the code on your computer, you can do that, or it will just be on the screen. I think some people were having trouble with this website, but if you just refresh a few times, it should work. So let's get into it. First of all, I'm going to explain the problem. So this is a problem we're going to try to solve with a neural network, and it's kind of it's a real-world problem, but it's a simplified real-world problem, so we have enough time to get through everything, and so you can understand all the components of it. So you have to imagine a scenario. So imagine the situation where you go to a country you've never been to before, and you see a stoplight. And you don't know, there's 3 lights, but you don't know which configuration of lights means to walk and which configuration of lights mean to stop. So since you're a programmer and a data scientist, you decide you want to collect some data. So you just sit there and watch, and you observe whether people stop or walk. So after a little while, you collect this information. So you can see this is the first stoplight, and that configuration of lights with the 2 on the side on and the middle one off, people stopped. And then you see this, people walked in the second configuration of lights, and then the third was just this one on, a person was stopping. So you're trying to figure out which configuration means walk and stop, but this isn't quite enough information, so you keep looking and you collect all this information here. And so we're trying to we collected the information of what we know and what we want to know. So what we know is the configuration of the stoplights. What we want to know is whether they mean to walk or stop. So we're going to use this data and see if our neural network that we're going to develop can figure out which configuration of lights means to walk or stop. Now this is a simple example, so hopefully you can kind of already see a pattern that the middle light is perfectly correlated to whether you should walk or stop, and actually the left and right light don't have anything to do with whether you can walk or stop. So when we develop our neural network, we're not going to tell it that information. We're going to see if our neural network can learn on its own that the middle light is perfectly correlated to the walk and stop data. So to make a neural network, we cannot just put in these notes or this picture here, so we have to convert it to numbers. So this is how we're going to convert our street light data to numbers. So we're going to make, if the light is on, it's a 1. If the light is on, or if it's off, it's a 0. So you can kind of see how these correspond to each other. So we've got this new data set, and we're going to use it to create a neural network to solve it. So I'm going to go over to my code editor here. Now, this is something called Google Colab. And Google Colab, it's basically like an online code editor for Jupyter Notebook. So if you got, I don't know if you're familiar with Jupyter Notebook, but it's used a lot for deep learning and machine learning. And this is an online version, so you don't have to have anything installed on your computer. And so it makes things a lot simpler when you're testing things out here. So I'll zoom in a little bit more. So this is where I'm going to start typing code. If you want to follow along, you can, or you can just look up at the screen. But the first thing we're going to do is import NumPy as NP. Now, maybe I'll... OK, you guys can see that? OK, so before we didn't use NumPy, but now we're going to use NumPy, and that's going to help with our multiplication. Remember, before I showed you that vector matrix multiplication function, we're not going to need that because NumPy has that built in. And that's the only thing we're going to import. The rest of it's just going to be straight Python. So now we're going to have our weights array. And I'm going to do mp.array. And the mp.array means it's a NumPy array. And this allows us to do special operations with it, like the vector matrix multiplication and stuff like that. So a lot of neural networks, the weights are going to start off randomly. And so I thought this would be a cool chance for some audience participation. And I'm going to see if you guys can give me some numbers. They have to be between -1 and 1. So give me a decimal point between -1 and 1. So does anybody want to call out a number for our first weight? 0.7. Okay, how about 0.7? And then we need another, it has to be between -1 and 1. Anybody else have another number? 0.2. Okay. And then our final number. Okay, so this was just a fun way to get random numbers so you can see later that it kind of doesn't matter what you start your weights out as, your network's going to be able to learn and get to the correct weight with just random weights. So the next line is the alpha. And we talked about that a little bit before. The alpha helps make sure your network doesn't get out of control. And the whole point of the network is to get our error to 0. But sometimes the error can start going up instead of down to 0. And the alpha will make sure it doesn't go out of control like that. So now we're going to import our data that we collected. So it's going to do mp.array. Now, I'm going to be this is going to be a vector or a matrix, so that's an array of arrays. And I'm just going to be typing in this information. I kind of have some notes here, but this is directly from the other slide of what this is going to look like. So this is kind of sometimes the tedious part of machine learning and data science is like dealing with the data and inputting data, but it's just a part of it is actually just trying to put everything into the network. And usually you're not going to be having to type in the data. You're usually going to get it from some other source, so it may not be you typing in every single number in the data set. Let's see. 1. And at some point, you may see me type something in wrong that it's obvious that it's wrong. So feel free to let me know, like if I spell like a variable wrong or something like that. OK, so if we go back to our data, this should look just like what we typed in right here. And now our next piece of information is our walk versus stop array. So this is, again, information we collected in the real world in this example. And we're going to do another mp.array and then pass in the array, which is going to be 0, 1, 0, 1, 1, 0. So again, that's the walk versus, if we actually have to go back a slide. So this is, anytime it's 0, or stop is 0, 1 is walk. OK, there we go. And then we can start with our iteration. So in the last example, before the break, I showed you a single iteration. But in this example, we're going to do an iteration of 40. So I'm going to do for iteration and range 40. Now, like I had said previously, sometimes you could have hundreds or thousands of iterations. And the whole point is that every time we go through an iteration, the error gets closer and closer to 0. And the way you figure out how many iterations to do is just through trial and error. So from preparing for the talk and other experiences, kind of trying out different things, I found out that in 40 iterations, this network should be able to get the error to 0. But there's not really any magic number. You just have to try different things and see the results and see how long it takes to get to 0. So now we are going to have a variable called error for all lights, and it's going to be set to 0. So we need to figure out the error, because the whole point is to get the error to 0, so we have to have something to collect the error. So we're going to be adding to that error later. And now I'm going to have another iteration for row, index, and range, and then it's going to just be the length of the stop verse walk array. So we're going to do something for every element in this walk verse stop array. And the number of elements in the walk verse stop array is also the number of arrays or vectors in the streetlights array. So we're going to do something for each one that you'll see in a second here. So in our last example, just like in our last example, we need an input and a goal prediction. So this is going to be pretty similar. The input is going to be from the streetlights array, and I'm going to put the row index. And then the goal prediction is going to be from the walk versus stop array. And that's going to be the row index. So you'll see we're going to iterate through each one, because this array corresponds to this number, the second array corresponds to the second number, the third array corresponds to the third number. Okay, what part? Okay, the space after what? Oh, stop versus walk. I should definitely. Oh, like is this what you're talking about?
No. Walk versus stop.
Oh, yeah. Okay. Thank you. I don't know. I was looking at it for some reason. I was thinking there's a spelling error, so I was like, what's spelled wrong? So yeah, thanks for pointing that out. So this is an example of what I was talking about. I'm going to make some mistakes, but luckily I have the audience here to help me fix these mistakes here. Okay. So now we have our input and our goal prediction. We can make our prediction. So let me see if I can you guys still see down at the bottom of the screen there? Okay, so our prediction. Now, if you remember before, when we had our prediction in the first part of the talk, I showed that we called our neural network function. And our neural network function just multiplied the input times the weight. So instead of creating a neural network function, we're just going to do the input times the weight. But we're going to use NumPy. So this dot function just multiplies input times weights, and it can multiply a vector times a matrix. So we're getting the prediction the same way as from before. And now we have to calculate the error. Let's see. Okay, there we can see a little better. The error is going to equal prediction minus goal prediction. And that's the same as before. So that's how we figure out how far away our prediction was from what we thought it was going to be, is the error. And then also, oh yeah, one last thing, we have to take that to the power of 2. So remember, the point of that is to make sure the error is positive. If you square it, it's going to be a positive number. And then also, makes big errors even bigger and small errors even smaller, and that's actually something we want because it will get to the correct answer even faster. So now we are just going to add to our error for all lights. Let's see, error for all lights. And I'm just going to do plus equals error. So we're just collecting all the errors into the error for all lights. So we're getting an error for each one of the walk for stop array, and we're putting them all together because we want the collective error to get as close to 0 as possible. And then we're going to calculate the delta. And that's going to be prediction minus goal prediction. This is just how far away our prediction is from our goal prediction, and it's considered the raw error. This is the same as before. And now we are going to calculate the weights. Now, in our previous example, the weights equaled weights minus weight delta times alpha. And we're going to basically have the same thing here, but we're going to, instead of creating the weight delta variable, if you remember from before, we're going to kind of put it in line, and it's going to be weights minus alpha. Oh, I need a parentheses here. Times input. So before, the weight delta was input times delta. And instead of making that weight delta variable, we're going to put it right in line. So weights equals weights minus alpha times input times delta. So that's the same as before. And now we're going to just print out some data. So this is actually the whole code. And so I'm going to print out some data here, and then we'll see what happens. So we're going to do, we're going to print the prediction. So we want to see the prediction variable, and I'll just do the string of prediction. Now I'm going to use some copying and pasting here. The prediction will do for each of that iteration, but the next two we'll put in to this next loop. Let's see. Yep, that lines up right.
You've got the parentheses on the last two-third weights, weights calculation.
Oh, right here?
Yeah.
Okay, thanks. I appreciate that. Okay, so now we have weights and weights. And then we'll print out the error. Oops. And the error. Okay, so we're about to run this code and see what happens, but before we run the code, I'm going to go back to the slides. Okay, so this diagram demonstrates what our network looks like. So we have 3 inputs, and then we pass them through these weights, and then we're going to get an output, which is the walk versus stop. Whether the output is going to show whether those inputs mean to walk or stop. So that's the whole point of our network. We're trying to learn from, do these inputs of the light mean to walk or stop? So that's what we're going to do here. Here we go. I'll just run this code. And it's going to take a little bit, but we should see, if I didn't make any spelling mistakes, we should see some stuff appearing at the bottom here, which is the data. Okay, so you'll see at the first, the prediction doesn't really correspond to anything at first, and the weights are going to be pretty similar to the weights we passed in at the very beginning. So you can see here are the weights. So we have 0.6, 0.4, negative 0.2. That's pretty close to the weights we started with right here. But if we keep going down, remember we did 40 iterations, so every time it gets to the error, we're to the next iteration. So the error starts at 0.3. We're trying to get as close as possible as 0. So if we just keep going down, we're not going to look at every single iteration. We're going to just kind of go down to the bottom and see what we've gotten to. Okay, so here's the last thing that we want to look at. And if you look at the prediction, this number is very close to 0. Then the second one is close to 1. Then we have one close to 0, 1, 1, 0. So if you remember, this actually is the same as our stop versus walk. So we have the stop is 0, 1, 0, 1, 1, 0, and that's what the prediction ended up being close to, 0, 1, 0, 1, 1, 0. Now that's not necessarily super exciting because we actually gave the network that information, so of course it's going to be able to figure out that information because we put it right in the code. Another thing I kind of should have showed you first was the error. This is a number very close to 0. It starts with a 3 point, but then when you see this is just like an exponent that makes it it's a really small number, very close to 0. So, and that's the whole point of our algorithm, is trying to get the error to 0. So what's really important to look at is the weights. So if you see the weights, these weights correspond to each light. So the first weight is close to 0, the second light is close to 1, and the third weight is close to 0. So 1 means it's perfectly correlated, and 0 means it's not correlated at all. And if you remember from our diagram, the middle light was perfectly correlated on whether you should walk or stop, and the right and left lights were not correlated at all. So there was no point in the code that we gave the program that information. But somehow it was able to learn that the middle light was perfectly correlated and the outer lights were not correlated at all. Now in this example, it was something that you can easily figure out just by looking at the data, which one's correlated. But you can just kind of imagine in a more complex data set, you may not be able to figure out how the data is correlated just by looking at it. So you use the exact same type of ideas to make an even more complex neural network, and so you can actually learn things that aren't as easy to just learn just by looking at the data. So our network, like I said, our network correctly identified the middle light by analyzing the final weight positions of the network. So to think about how it identified the correlation, it was in the process of gradient descent. Each training example either is going to assert upward pressure or downward pressure on the weights. So on average, there was more upward pressure for the middle weight and more downward pressure on the outer weights, so they got to the correct numbers. So this is pretty cool, and now I'm going to show you something even a little more complex. So the next part of the talk, instead of live coding, I'm going to show you some code that's already written that's pretty similar to the code we already had, but I'm going to introduce a few more concepts. First of all, I want to tell you that some of the concepts could even be a whole talk to themselves, so I'm going to do my best to quickly overview the concepts, but some of the things you'll just kind of get a taste of so you can learn more about on your own later. But the reason why I'm going to show you one more program is to talk about the deep part of deep learning. So nothing I've showed you so far is actually deep. So deep refers to one or more hidden layers between the input and the output layers of a neural network. So if I go to my code here, so our input layer is right here, our output layer is right there, there's nothing in between. But if we look at this example, this is a true deep neural network because we have our input layer that looks the same. There's 3 on the input and 1 on the output for layer 2, but now there's this middle layer which is a hidden layer. And since there's 1 or more hidden layers, this is a deep neural network. So you may be wondering, why would you even need a hidden layer if our other network was able to correctly predict the correlation between the lights? Because we're going to use the same example from before. So if you remember the data, the middle light was perfectly correlated with whether you should walk or stop. But if the middle light wasn't so perfectly correlated, our network would have had a much harder time figuring out how the input was related to the output. So for instance, if our training data looked like this, our other network wouldn't have worked so well. If you look at this, so the numbers in red are the light information, whether the lights are on or off, and then the numbers in black are the stop or walk information. So you can see this the first 3 up here means to walk, then we have walk, stop, stop. And one thing you'll notice is that the output data is not perfectly correlated with any of the rows. So this is where you need to have a hidden layer. Because since our input data set does not correlate with our output data set, we're going to use our input data set to create an intermediate data set that does have correlation with our output. And this intermediate data set is our hidden layer. It's almost going to be like two neural networks. It's going to be from layer 0 to layer 1 is going to be one network that runs just like before, and then the output to the layer 0 to layer 1 network will become the input to the layer 1 to layer 2 network. So let me show you. To remember how to get to the other code here. Okay, so can you guys see this all right? Even in the back? Okay, so a lot of this is going to look pretty similar here. We're importing NumPy as MP, and then this line right here, just make sure, we're going to be using random numbers in this code, and that line just makes sure the random.seed, make sure every time we get random numbers, it's the same random numbers. So a lot of times when you're dealing with neural networks, you're using random numbers for the weights, but to make sure the output is always the same, even though you're using random numbers, you can make sure that every time the code runs, the random numbers were the same random numbers that you used last time you ran the code, and it helps for like comparing to make sure the results are exactly the same. So this is this is an activation function. It's the relu function. We're going to pass our data into it, and it's going to return x, or it's going to return the data we passed in if x is more than 0, or return 0 otherwise. Now, this is, it's called an activation function because it activates some input by returning the input and deactivates other input by returning 0. This code is going to show a 3-layer neural network, and by turning any middle network off whenever it would be negative, we allow the network to sometimes have the correlation from various inputs and sometimes not have the correlation. So it's impossible for a 2-layer network to sometimes allow this input to correlate and sometimes not allow it to correlate. So it adds more power to 3-layer networks. So this sometimes correlation is important for things to work correctly, and this is one of the areas that, like I was saying, could get a whole talk to itself as activation functions and how they work and why, but I'm just going to kind of leave it at that for now, and that the activation function is important to make it sometimes correlate and sometimes not correlate. Uh-huh. So yeah, so how this works is, yeah, if x is more than 0, so this is going to end up, I think that's going to evaluate to 1 or 0. So then we multiply, so x is more than 0, that could, if that's true, it's 1, if it's false, it's 0, and then we just multiply that by x, and if it's 1, you know, we're returning x, if it's 0, we're returning 0. Did that answer your question? Oh. Okay. Okay. So the relu2 deriv function is next, and this returns 1 when the output is more than 0 or 0 otherwise, and that's the slope of our relu function, or its derivative. And you'll see later how that's important. So the next two, this is just inputting the data, just like we did before. We do have the .t, that's a NumPy thing. It's the transpose operator, and it just changes. So you have a matrix, which is going to have like almost like an x and y coordinate. So if it's a 3x4 matrix, the transpose operator would make it a 4x3. Or if it's a 1x4, it'll become a 4x1. And when you're multiplying a matrix and a vector, it matters which kind of direction the matrix is, if that makes sense. And so the alpha is same before. Again, sometimes you have to kind of try out different things to figure out what is going to work. And the hidden size is 4. So if we go back to our diagram, you can see that our middle layer has 4 nodes. So that's what this hidden size equals 4 is. There's 4 nodes. And then here is our weights. So, whoop. Okay, let me get back to that code here. I accidentally did the keyboard, the mouse shortcut for going back. So if we go to our weights here, before, this is where we had the audience participation, and I had people shout out different weights. But now we're going to get truly random weights because we have a lot more weights. This is going to be a matrix of weights, and the size of the matrix, like the matrix is similar to this. This is a matrix right here up top, a 3x4 matrix. And this is going to be a 3x4 matrix, and this is going to be a 4x1 matrix, and each number in that matrix is going to be between -1 and 0. And the reason why we have 3x4 is because you can see there's 3 nodes by 4 nodes, and then we have 4 nodes by 1 node. So the size of the weights has to correspond to the input and output layers, because you can see that there's a weight between layer 1 and layer 0, and there's weights between layer 1 and layer 2, and the size of the weights have to correspond to those layers. So now you can see we're gonna iterate 60 times. And then we're going to keep track of the error, just like before we were keeping track of the error. It's just called something different. So in this code, there's going to be a lot of things that are pretty much just like the code that I just did for the live coding, but the names are slightly different. So layer 0 here, this is the same as the input from before. So we're just getting the first street light, which would be this matrix right here, this vector right here. And this is just a kind of fancy way of saying that we're going to get a nested array. So instead of an array of 101, it will be an array of 101. So there'll just be like if you outputted it, there would be an extra array on the sides. There we go. So so that just makes the kind of the math work to have an array of arrays, but it's just getting the first array from the streetlights. And then layer 1 here is going to be the same as the input and the same as the prediction from before. Remember the other network, we had 1 input, and that input had 1 prediction. But in this neural network, it's basically 2 neural networks. There's two networks. There's layer 1 to there's layer 0 to layer 1, and there's layer 1 to layer 2. So the prediction or output from layer 0 to layer 1 becomes the input from layer 1 to layer 2. So this layer 1 is the input and the prediction. So just like before, we're always just to get a prediction, you always multiply the input times weights. So that's what this is. It's another NumPy function to just multiply the things that you pass into that function, layer 0 and weight 0, 1. That's what you're always doing for your prediction, multiplying inputs times weights. Then we run it by the ReLU function, which will selectively activate, like we talked about before, and it's only used on hidden layers. So we're not going, layer 2 is not our hidden layer. Layer 2 is our output layer. And which is the same as our prediction from before. And again, we're just multiplying the input times the weights. So the input is layer 1, and the weights is weights 1, 2. So this is the same thing we've been doing all along to get the prediction. From the first talk, from the very first code example, this was the neural network. We had a neural network function that just multiplied weights times input, and that's exactly what we're doing here. So now we have to get our error. So our error is we have our layer 2 error here, and we're going to calculate that pretty much just like before, but we have different names. So before, the error was prediction minus goal prediction squared, but now the prediction is that layer 2 variable. The goal prediction is getting something from the walk versus stop array, and then we square it. So error is always prediction minus goal prediction squared, and then we're going to do a plus equal, so we're going to add up all the errors together into our layer 2 error variable. Okay, so the next thing is our delta. This is basically exactly like the other example. So we have the layer 2. So this is just input, or wait a second. Yeah, input minus goal prediction minus goal prediction. So layer 2 minus walk for stop is the same as prediction minus goal prediction. And remember, the goal here is error attribution. It's all about figuring out how much each weight contributed to the final error. So in our first 2-layer neural network, we calculated a delta value, a delta variable, which told us how much higher or lower the output prediction is supposed to be. So we're calculating that in the same way. So now we have how much that we want the final prediction to move up or down. That's the delta. And now we need to figure out how much we want each middle layer, layer 1 node, to move up or down. So one thing that's interesting about this is if we go to our diagram, we can see there's an order: layer 0, layer 1, layer 2. But in our code, we're going to calculate layer 2 first and then layer 1. So we're not calculating it in the same order as you would normally think going through the layers. This is another really big concept called backpropagation. Let me zoom out so you can see all the notes I have here. So in backpropagation, the layer 2 delta is backpropagated to the layer 1 delta. And this is going to give us a weighting of how much each weight contributed to that error. That's supposed to be the word error. Oh, it is. It's just off the side of the screen. Okay, so we need some way for our layer 2 weights to impact layer 1, because we need to update everything. So that's what backpropagation is. And so this is another pretty big concept. I mean, backpropagation could be a whole talk of its own, but it's all about taking information from later on in the network and passing it back to the earlier in the network, so it can use that information when it's making the calculations. And let's see, if there's one more thing we need to talk about. So this is for the layer 1 delta. Here we're just using this dot function to multiply layer 2 delta by the weights, and we have the transpose operator. But then the final thing is this ReLU2deriv function. So if the ReLU set the output to layer 1 to the layer 1 node to be 0, then it didn't contribute to the error at all. So when this was true, we should also set the delta of that node to be 0. And multiplying each layer 1 node by the ReLU2deriv function accomplishes this. The ReLU2deriv is either a 1 or a 0, depending on whether the layer 1 value was more than 0 or not. So now we're going to update the weights, and we update the weights just like we did before. So for each weight, we are going to multiply its input value by its output delta. And so it's just weights 1, 2 equals weights 1, 2 minus, wait, I'm thinking, yeah, weights 1, 2 equals weights 1, 2 minus alpha times, and then, so this is just how we calculated the weights before, where you multiply the input by the delta, and then you multiply that by the alpha, and then that's just how you update the weights. So again, this code is all online, so you can kind of review it later. Like some of this stuff, it kind of takes going through a few times to really see how it all goes together. But you'll see that we're updating the weights in the exact same way as we were in the other live coding session that we did. So down here, this is going to just make sure that we're only going to print this information just every once in a while, so every few iterations. So when we run this, it's only going to give the information every few iterations. So I'm just going to run this right now, and I think it had that from last time I ran it. But if the main thing to look at here is that if we go to the bottom, our error gets very close to 0. So that's the whole point of learning. Learning is trying to get our error as close as possible to 0. Now, if you remember before, that meant that our weights were making a correct prediction. And in this case, it's the same. Now, I'm kind of getting close to the conclusion of kind of why all this matters. So I mean, we could probably talk about this code for a few more hours to explain it, every little part, like the back propagation and the weights. But I kind of want to kind of step back a little bit and give kind of an overview of the point of why we create intermediate data sets that have correlation. So I'm going to go back over here. Okay, so consider this image of this handwritten 4. It's kind of blown up. It's supposed to look like the number 4. And if we had a data set of a bunch of images of handwritten digits, and they were all labeled like 0 to 9, if we wanted to train a neural network to take the pixel values from this image and predict that this was a 4, our 2-layer neural network would have never been able to do it. So there's no individual pixel in this here. So there's no individual pixel that perfectly correlates with whether it's a 4 or not. Just like in our second example that I just went over, there was no light combination that perfectly correlated with walk or stop. So there's only different configurations of pixels that correlate with whether or not this is a 4. So this is the essence of deep learning. If I go to the next slide, you'll see how this would work with kind of the multiple layers, where deep learning is all about creating intermediate data sets or layers, where each node in an intermediate layer represents the presence or absence of a different configuration of inputs. So in this way, no pixel has to perfectly correlate with whether or not it's a 4 or not. Instead, we have these middle layers that they attempt to identify different configurations of pixels that may or may not correlate with the 4. So we go through a lot of different layers, and finally it finds which layer correlates, if it finds a configuration of pixels that correlates with whether it's a 4 or not, and then it outputs that this is a 4. So the presence of many 4-like configurations would then give the final layer the information or correlation it needs to correctly predict whether the digit is a 4. So we can take our 3-layer network and continue to stack many, many more layers. Some networks even have hundreds of layers. And each neuron plays its part in detecting different configurations of input data. So you could start with, like we started with these input of 3 layers, but the hidden layers could get bigger and bigger and bigger till it finally has what it needs to correctly predict the output layer. So I'm hoping that just kind of seeing this 4 example helps you kind of see how adding additional layers can help you get the final prediction, where you don't need, just like our stoplight example, you don't need the perfect correlation to figure out the final answer. You can make other layers and other layers after that that finally get the correlation to get the final answer. So I'm getting to the end of the talk here. So I'm hoping you, just by this talk, you got a good introduction to deep learning and neural networks, and you saw by the examples how we were able to write a neural network that actually learned what we're trying to learn. And then I also hope you started to understand how hidden layers can give your neural network even extra power to figure out things it would not have normally figured out. So yeah, thank you for coming to the talk, and I'm open for questions right now.
Yeah, thank you very much. That was really interesting. I've tried to also build something for a couple of times, but I think I need to practice more. Okay, questions? Yeah.
Thank you for your speech. Maybe I haven't understood, but how we can select a number of layers and a lot of layers, is it always good, or we have to find a gold number, an ideal number of layers?
Okay, so it sounds like the question is like how we decide how many layers that we need to have. This answer is similar to a lot of things in deep learning, which is just trial and error. So sometimes it's you just so generally you have certain like you try maybe a smaller number of layers, and you would kind of keep adding layers until eventually, I mean, you know you're doing it right if you get your error to get to 0. So a lot of things with, so it's almost like there's not like a one size fits all where you're always going to use this number of layers, and you're always going to use a different number of layers. It just depends on the data set. It depends on just having experience doing it many times. So you would just try a certain number of layers. If that doesn't get your error to 0, then you would increase it. You would like keep increasing it until you can figure out something that works.
Thank you. With what maximum accuracy can neural network be made? What does with accuracy depend on? So how to create a maximum accuracy neural network?
So the question is how you would create a neural network?
How to create the most accuracy neural network.
Okay, so it's not, you're asking how to create the most accurate neural network and increase the accuracy?
Accuracy.
Okay, yeah, so again, so there, in our neural network code, we had various things that we can update to get it to be more accurate. So so we have kind of the basic code, and so a lot of neural network, you're going to use some similar functions, and you're no matter what data set you're using, you're often going to be using some similar concepts, but there's different things that you tweak to create the accuracy. Now in this example, all the things had already been tweaked beforehand, so you didn't get to see the process of tweaking them, because I just wanted to show you like one that already worked instead of one that doesn't work, then we continue to get it to work. But some things you would tweak would be the hidden size, which would be you can increase the hidden size, but if you increase the hidden size, then you would also have to change the weight. So the weights have to correspond with the different layers, and then you could also increase the iterations that you're doing. You can increase the alpha or decrease the alpha. So as with a lot of things, there's a lot of trial and error so the first time you run the network, it probably is not going to be super accurate. The error may not get to 0, and you're just going to have to try running it again with a different alpha or a different hidden size or a different number of iterations, and you just keep trying different things until you can finally get to until the network can give you the results that you're looking for.
Thank you.
Yeah, so I'm not a specialist in deep learning, obviously, but I wanted to ask, like, I attend meetups, like open data science meetups and something like that. But they like to describe deep learning architecture by, these graphs of a lot of layers. And there's this issue which I don't quite get. There's like different ways of connecting hidden layers. And to what it corresponds. Does it correspond to activation functions, which like, what is the connection of hidden layers? Is it corresponds to activation functions or something else?
Yeah, I guess that the activation function would impact how they're connected, because the activation function decides which nodes kind of get passed on to the next node. Because in the ReLU function is one activation of many different activation functions that would kind of determine which data kind of gets to continue up the stream of the neural network. So I think that would be a key way that the layers would be related to each other differently, like what you're saying.
Thanks.
Okay.
You know what, there was one more thing I forgot to say, which is, so I have this course with Manning Publications, so if you want, there's a, Manning Publications made a promo code just for this conference. So
Yay.
If you want to get 40% off all products of Manning Publications, you can use this code, and it's also on my website, so consider getting the course if you want.
Perfect. Maybe more questions now about the course? No? Okay, so thank you very much. That was nice. And once again, you're choosing the best question.
Okay, I'm gonna choose this guy back here.
Okay.
Yeah,
Okay.
I liked his
Thank you.
question.
Аплодисменты, ребята, давайте. Вот, отлично. И